The other main type of problem that you'll see in the statics unit are ladder problems. Um, and I remember taking this class as a freshman, and these problems being kind of the bane of my existence. I think I might have mentioned that in an earlier video. Because there's a lot to account for, and if you aren't as strong in trigonometry as you'd like to be, this is going to be the place that gets you, because keeping track of these angles can be a bit complicated. So I'm going to walk you through this, and show you the best way to try and make sure that you account for everything, and to make sure that you get your trig functions right. Okay, so we're going to start out just like we've been solving all the other statics problems. We want to find our normal force on the floor. We know that we have a frictional force on the floor. We have the gravity of the ladder. And actually I'll call the mass of the ladder m sub l. So we have m sub l g. We have the mass of the man, g. But that's not it. We also have a force from the wall on the ladder. And there could potentially be another force. We could have a frictional force between the ladder and the wall. In this case, we're going to neglect that, just because it's an unnecessary complication. Once you can solve this problem, then you can add that part in later and solve that as well. But I think we've got enough parameters in this that we can just work with what we have. And so we're going to say that there's no friction between the ladder and the wall, but there is friction between the ladder and the floor. So a problem like this might be asking you, if we know the coefficient of friction mu between the floor and the ladder, what's the lowest angle that we can set the ladder so it doesn't slip? And as a function of the distance that this guy is. So if he's a distance x up the ladder, and the length of the ladder we'll say is L, then as a function of the distance he climbs up his ladder, what does the angle need to be? Or equivalently, if we know the angle of the ladder, how far can he climb up before he falls? Okay, so again, we'll start this exactly like we've been solving our other problems. The first thing we do is we find our net forces. And so we see, going from left to right, so we have a normal force. The normal force is going up. We have a frictional force going to the right. We have a gravitational force acting on the center of mass of the ladder. We have a gravitational force acting at the place of the man. So we should have had an L here for that M. And we have a force on the wall acting to the left. And of course, the sum of all of those forces is going to be 0. So we quickly see our first relation, that the force on the wall is equal to the frictional force, in magnitudes of them. And we also see that the normal force is mass of the ladder plus of the mass of the man times g. So neither of those results should be very surprising. It's just saying that there's one force up and 2 forces down, and there's 1 force to the left and 1 force to the right, and so we balance those out. Okay, so now we go to our torque equation. And again, we have no contribution from the normal force to the torque. We have no contribution of the frictional force because, I guess I should take a second and explain why. So if you can think about if the ladder falls, the way that it's going to fall is it would pivot around this point here at the bottom. This is where it would be rotating about, because the top would basically be kind of kicked around like this, and this point would just be pushed out. So there's a translation and a rotation around that point. And if you were an engineering section, I might actually make you find out what that would be to find out the final velocity of the ladder as it went toward the floor. But I think that's a little bit much for this section. So so we look at the net torque. So again, because these two forces are acting at the pivot point, there's no torque due to them. Okay. Now we need to find the torque for gravity. And again, we know that we want the component that's going to be perpendicular to the ladder. So we redraw our picture again. Well, first we'll get our angle straight. So if we want this to be the part that's perpendicular to the ladder, we see that this angle is theta. So this angle is 90 minus theta, because we have a triangle right here. And so if we have a triangle, these two angles, since this angle is 90, these two angles also have to equal 90 together. So if this is theta, this is 90 minus theta. Well, notice now we have another 90-degree angle right here, which means this angle is also theta. Because if this is theta, then this is 90 minus theta. So we can redraw our ladder down here. We have our mass of the ladder G. We have our mass of the man G. And we have our force from the wall. So again, we can split this up into two components. We know this is theta, and we don't want this component because the cross product is going to vanish for this. We only want the perpendicular component to the ladder, and it's going to rotate. So this is going to be trying to get it to rotate around this point clockwise. Similarly, we do the same thing because we know this is the same angle theta, right? Because these vectors are parallel, so this is the same angle here, and this is also trying to rotate in that direction. So now we just need to find out where theta is in terms of the force on the wall, because we know for the force on the wall we want this component. So if we go back up here and look, we see that if this is theta down here, this angle is 90 minus theta, which means this angle is theta. So here we see that now we have theta is here. So now going back to our torques, the torque due to the gravity of the ladder is going to be at a distance L over 2. So we have L over 2 mass of the ladder G, and that again is going to come with a minus sign because we're rotating it clockwise, and it's the Z component again because we're in the XY plane, and so this is going to be the component that's going into the board or into the computer screen in this case. For the mass of the man, it's going to be the same thing, 0, 0 minus x mass of the man G. Now for the force on the wall, it's going to be positive, and you see that we want the sine theta component of it. So it's going to be 0, 0 L force on the wall sine theta. Okay? Oh, and I'm sorry, I left off. This should have a cosine theta, and this should have a cosine theta. Again, because we only want this component, the cosine theta component of both of these. So they should have both had a cosine theta on them. And we know that this is equal to 0. So this again just gives us a simple equation that we can solve. we say that L times the force on the wall sine theta is equal to L over 2 mass of the ladder plus mass of the man x times g cosine theta. So in other words, the force on the wall is g over L cotangent theta, L mass of the ladder over 2 plus mass of the man x. So this is telling us the force on the wall. What we actually wanted, though, if you remember, is we wanted to find the angle theta. We wanted to find theta to find out how steep we can make this ladder so that the man doesn't slip if he goes up some distance x. And so if we wanted to do that, well, we know that the force on the wall is also equal to the frictional force, which is equal to the coefficient of friction, mu, mass of the ladder, mass of the man, times g. So in other words, the cotangent of theta is equal to mu mass of the ladder plus the mass of the man. G's cancel out. We multiply by an L divided by L mass of the ladder over 2 plus mass of the man x. And then we can take the inverse cosine to find the angle. Similarly, we can reverse this, and if we know the angle, we can solve for x and find out how far the man can move up the ladder. Okay, and so the last thing, let's check our units. So we see that we have a mass times the distance on the top and a mass times the distance on the bottom, so everything cancels out. We also see that this makes sense, right? We're because we know, we have the force on the wall balanced with the force of friction. That makes sense. And we know we have our equation for friction. We know that, and so we see that it's going to be the sum of the masses times the coefficient of friction times g, and that's what we expect. So everything makes sense. So you can see we had to go through a lot to get here. And perhaps the most difficult part is making sure you get these angles right when you're writing your vectors over here. But as long as you do that, and you just kind of follow this procedure and just step by step put all this together, then these problems that are actually really nasty, even for very good students, can actually become quite tractable, and there's something that that all of you can really do. So that's going to conclude this unit, and then the next unit we're going to start. We're going to take this, what we did here, summing up forces, but now we're going to say the sum of the forces isn't going to be 0. We're going to have some acceleration, and so we're going to start looking at coupled systems and things that are in motion.